What proven math fact surprised you the most when you learned it? As a high school calculus teacher of almost 30 years who has fine-tuned the art of simplifying mathematics for a large spectrum of learners, let me offer an answer that can be appreciated by a wider audience. I was discussing the graphs of and in a calculus class once, graphs that increase at a decreasing rate, eventually rising so gradually and imperceptibly that they appear to be perfectly horizontal. If you are unfamiliar, you can graph each on Desmos calculator. My students wondered how long it would take for each graph to reach the ceiling in the classroom. We placed the origin at the bottom left-hand corner of the whiteboard, marked off the x and y axes at 1-inch intervals, and performed a simple calculation for each graph to reach the 10-foot ceiling. The graph of y equals x minus square root y equals x traveled to the right about 1,200 feet before it finally reached the ceiling. That was expected. But the graph of y equals ln x y equals lane x rises so slowly that it would travel to the right trillions of times farther than the edge of the known universe and still would not reach a height of 10 feet. That shocked us all. Since I was flying to California the following week to visit my parents, and my father was a world-famous mathematician, I knew he would appreciate this fact. So I prepared an informal paper on the rise of various functions, exponential versus radical versus logarithmic, and couldn't wait to show him. My plane had just landed when my mom called and informed me that my father had unexpectedly passed away while I was on the flight. I never got to show him. Surprised me? Who cares? How about when Claude Shannon surprised the entire computer science community? It was the result of his famous 1948 paper, The Mathematical Theory of Communication. To get you surprised, let's set up the problem. The goal is to communicate a string of ones and zeros across a noisy channel. That means for each digit that passes through the channel, it'll flip that digit to the other digit with probability pp. How would you communicate a string to someone on the other end accurately? As is typically advised, start simple. Let's say we want to communicate one digit. Here's an idea. Repeat that digit 1,000 times and send that length minus 1,000 string through the channel. Then have the recipient interpret the most common digit as the digit you intended to send. The longer that sequence is, the less likely the recipient received an incorrect answer. But there's a cost. You effectively slowed the rate of communication tremendously by a factor of 1,000 to ensure such a low probability of error. But what about a length 10 string? We can probably do better than naively repeating each digit since we have more structure to play with. One mathematical fact that continues to surprise me is the fundamental theorem of arithmetic, even though I have explained the proof many times to classes of college juniors who intend to be math majors. Though it is called fundamental, most people have never heard of it, although every high school student really should know about it, even if they are not prepared to understand its proof. There are two parts to the theorem. The first is that every positive integer can be written as a product of prime numbers. That's something that many students learn about in school, sort of. For example, they can write 100 as 2 * 5 * 2 * 5. You might object and say that 11 is not a product of primes. But, from the point of view of mathematicians, 11 is the product of one prime, namely 11, so we, by convention, agree that every prime is considered a product of primes. The second part of the theorem is that every number can be written as a product of primes in a unique way. That's not quite true, because 6 can be written both as 2 * 3 and 3 * 2. However, if we ignore the order in which the primes are multiplied, every positive integer can indeed be written in a unique way as a product of primes. That to me remains surprising. I would like to think that there is some renegade number, maybe with 50 digits, that can be factored in two completely different ways. Why is that so unreasonable? It is not at all obvious that there is no such number, and it would be wonderful if some number refused to conform to the fundamental theorem of arithmetic, but surprisingly that can't happen.